secant pi in your calculator and be done? All right, let's look at a couple more derivatives. On number 12, we have two things multiplied. So the first thing I would see is this is going to be a product rule with f and g. So we have f prime g plus g prime f. So when I take the derivative of both of these, you'll see that they both have a power rule. Now, one thing I want to point out is the good news is there's no chain rule in this inside. Even though it's not x, the derivative of x plus 1 is still 1, and the derivative of x minus 7 is still 1. So I don't have to worry about the chain rule in this problem. So y prime, dy dx, whatever you want to call it. So I'll take the derivative of the first, which makes bring the 3/2 down, x plus 1. And then when I subtract the power, I'll get 1/2, because 3/2 minus 1 is 1/2, times the original g, so I don't change it. So x minus 7 to the 7th, plus g prime. So now I'm taking the derivative of the second function, which is going to be 7, x minus 7 to the 6th, and times the original f function, which is x plus 1 to the 3/2. And the good news is, since we don't have to simplify or anything, we'll just keep it just like this. Now 13 is a tricky one because there's no product, no chain, but what I do see is this has a couple chain rules. Because if I think of this function, this is essentially secant of x to the 7th all squared. So when I think about my outer function, it's actually a squaring function. So if you take the derivative of x squared, that's where you bring the 2 down and all that. But I'll have this inner derivative. So the derivative of this, f prime of x, since the outer function, you start with the outside function, is just a squaring function, I'll just bring that 2 down. And then I'm going to keep the inside the exact same. So I'm going to keep it as secant x to the 7th, and then it's going to be to the first power. But now the trick is I have to multiply by the derivative of that inside, which is secant. So if you remember, the derivative of secant is secant tangent. So I'll add a secant and a tangent of whatever it is. Now what's in the secant tangent, unfortunately, is x to the 7th. So I'm just going to keep that for both, but that's not x. So I'm going to have a third part of the chain rule, where I have to multiply by the derivative of the x to the 7th. So taking the derivative of the first inside gives me this, but since it also had an inside, it gives me that part here. So this monster here is my derivative. So always start with the outer function and kind of take it from there. All right, if we look at number 14, it says find the equation of the tangent line to the curve y equals x squared minus 4x minus 5. This is a very traditional calculus problem where we know that the slope of the tangent line is given by the derivative. So dy dx is 2x minus 4, nothing crazy about that. Now this one's a little different because what we usually do is we'd find the slope and we'd plug it in and kind of all that stuff. But we want it to be parallel to this line. Now the slope of this line is negative 12 because mx plus b, the number in front of x, is always your slope. Well, since this function, this derivative, is giving me the slope, I can figure out what x value this is going to occur at. So 2x minus 4 equals negative 12. So what I can do is I can figure out what that x value is. So that's going to give me 2x equal negative 8 and x equal negative 4. So this is kind of a little different part where you had to figure out what the x coordinate is, because we've done lots of problems where you find the equation of a tangent line at a point x equal negative 4. We just had to figure it out in this case. I'm not sure that would be on your final, but it's a little different variety. So anyways, we have this function. Now we want to find the tangent line at x equal to negative 4 will be the x value, and the y value, remember, we will plug negative 4 into my original. So y equals negative 4 squared minus 4 times negative 4 minus 5. So that's 16 plus 16 minus 5, which is 32 minus 5, which is 27. So I want to find the tangent line of -4 and at -4, 27 of this function. Now I know the slope is -12. I already kind of established that. But if I wanted to plug the -4 in here, I certainly could, and I could get -12 again. So now I just have to find my intercept. So y equals mx plus b. So the y is 27. The slope is -12. The x is -4 plus b. So that's 27 equals 48 plus b. So subtracting from both sides gives me a b of -21. So my final answer is going to be y equals mx plus b. And now the good news is if you want to check this, we could certainly graph it on Desmos or something and see if this line is indeed tangent to this graph at x equal -4. And if it is, then we're good to go. All right, let's look at 15. 15 says find dy dx in terms of x and y. This is our implicit differentiation. So if you remember this, this is where we had to, anytime we took the derivative with something that was different than x, we had to put our dy dx and then eventually solve for it. So if I look at this, the derivative of x squared is just 2x, nothing crazy there. The derivative of 3xy, this is actually going to be a product rule, so f prime g plus g prime f. So the derivative of the first function, the derivative of 3x is just 3 times y, nothing crazy there. But the second part, the derivative of the y function, is dy dx times the original f function, which is 3x. And then we have y squared, so the derivative of y squared is 2y, but we have dy dx, and then the derivative of 1 is 0. So in these kind of problems, this is where you have a couple terms that have dy dx, this one, and then a couple that don't. So you want to get everything that doesn't have a dy dx on one side and everything that does on the other side. So I'll keep the things with dy dx on this side, and I'll go ahead and subtract 2x and subtract 3y to the other side. So I'm subtracting these two terms that don't have the dy dx to the right. So now I want to solve this, so I'm going to go ahead and factor out of dy dx. I'll be left with 3x plus 2y equals -2x minus 3y. So then we could just divide to get dy dx by itself. So it's kind of an algebraic way to find the derivative. So -2x minus 3y divided by 3x plus 2y. All right, 16 is a really important problem. We spent a lot of time on this. Find the intervals of increase and decrease and concavity. So remember, increase and decrease are going to be the first derivative, and concavity we use the second derivative. Okay? And this is where we have our sign chart and all those kind of things. So don't forget about that. So if I take my derivative, that's my first step. I have a product rule again. You'll notice we have a lot of product rule. So the derivative of the first is 1 times e to the x plus the derivative of the second, but the derivative of e to the x is just e to and then times x. Now, if I want to find my second derivative while I'm at it, I certainly can. My second derivative, the derivative of e to the x is just e to the x. And then this is back to our original function. So we'll get the same first derivative when I take the derivative of it. So it's e to the x plus x e to the x, which I simplify as 2e to the x plus x e to the x. So let's do our increasing, decreasing first. So increasing, decreasing, we're going to use the first derivative. So I want to find out where the first derivative equals 0. That's going to get the critical points to do my sign chart. So I'm figuring out when is 0 equal to e to the x plus x e to the x. I'm just switching these to make it look a little better. So I can factor out an e to the x, and I'm left with 1 plus x. Now, e to the x is never, never, never equal to 0 because it's an exponential. So really, we're just looking at this one, which is only 0 at x equal -1. So my sign chart for increasing, decreasing is just going to have -1 on it. That's it. So I'll have an interval from -infinity to -1, and then -1 to infinity. So I'm going to pick a number smaller than -1. I'll go -10, and I'll pick a number big, 0. So if I plug this into the derivative, if I plug in -10, I'm going to get a negative number. I don't know what negative number, but I know it's negative. And if I plug in 0, I'm going to get a positive number. It's actually +1. So in this interval, it's decreasing. In this interval, it's increasing. So I would say it increases from -1 to infinity, and it decreases from -infinity to -1. And again, this is certainly something you could check on Desmos. Make sure that you do have the correct intervals. Obviously, you do need to make sure you show some work, because if you don't show the work, you will not get credit for it. Now, concavity, we can do the same thing. We just have to use the second derivative, which if you look at this, I can also, when I'm setting this equal to 0, I can also factor out e to the x. E to the x still never 0, so I'm just looking at this guy, which has a 0 of -2. And I'll do the same thing. I'll put my -2 here. So it's either going to be -infinity to -2 or -2 to infinity. So I'll pick a number smaller than -2 and a number bigger than -2. And I'll see what the second derivative is. So if I put the second derivative in, I'll get a negative and then a positive. You can plug it in and check for yourself. So this is going to concave down from -infinity to -2, and it's going to concave up from -2 to infinity. Remember, the concavity is kind of the curvature, how it's slanted. Is it curving up or is it curving down? So a big thing to remember is first derivative for increase, decrease, second derivative for concavity. All right, let's look at one more problem. This is one of the word problems that we've had. This is a minimize and maximize function. And this is one that I could certainly say there may be a very, very, very similar problem on the final. Very similar. Very similar. So a farmer wants to construct a rectangular field with 6,000 square yards. So a rectangular field with 6,000 square yards. So the area has to be, or 60,000. I missed a 0 there. So we'll call these dimensions x and y. So I know the area, x times y, has to be 60,000. Perfect. He wishes to enclose the field to be divided into 3 sections with both dividers parallel to one of the 3 sides. So we need 2 dividers here. Now the good news is, if you look at this, all these sides are x because they're the same length, and these 2 outer sides are y. Okay, so that's kind of our picture. Now the outer fence costs 20 yards for a foot. Or yard, pardon me. So this one, this one, this one, and this one all cost $20. But it's cheaper for the fence inside. These 2 only cost $10. So we're trying to minimize our cost. So if I try to do a cost equation, the cost, well, I need $20 for the outer edge. So it's $20, and how much fencing do I have? Well, I have 2x plus 2y. That's just the top 2 and the side 2. Plus $10 for those 2 in the middle, for the 2 red x's. Those are both going to cost $10. So that's my cost equation. That's what I'm trying to minimize. So if I simplify this, I get 40x plus 40y by distributing plus 20x. So the cost is 60x plus 40y. So those are my 2 equations. I have this one and I have this one. Now this is very, very traditional optimization or minimization. We're going to solve for 1. So up here, I'm going to solve for y, although you certainly can solve for x. So y is going to equal 60,000 divided by x. And then I can plug that in down here. So my cost is going to equal 60x plus 40 times 60,000 over x. And since I'm going to take the derivative, I'll clean that up. I'll make it 60x plus 24,0,0,0,0. And I'll make it x to the negative 1. Because obviously, if you remember these kind of problems, once we get our equation and we make it just 2 variables, c and x, we're going to take the derivative and see where it equals 0. And that's generally going to be where our cost is minimized. So c prime is going to equal 60 minus, because I'm taking the negative 1 down, 24,0,0,0,0 x to the minus 2. And so I just have to figure out when that equals 0. So 0 equals 60 minus 24,0,0,0,0 x. Well, let's just make it, since it's x to the minus 2, I'll put it on the bottom there. So there's a million ways to solve this now that we have this equation. So I'm going to go ahead and add this term to the other side. So I'm going to get 24,0,0,0,0 over x squared equals 60. Simplest way is to multiply x squared to both sides, because these will cancel. So I'll get 24,0,0,0,0 equals 60 x squared. And then I'll divide by 60. So I get that to cancel. So I get 4 with 3 zeros. And then I could, of course, take the square root. Technically, my thing is plus or minus the square root, but we know you can't have a negative fence length. So our fence, to minimize it, we need x to be square root of 4,000, whatever that turns out to be. All right, I would encourage you to look at this. I would encourage you to watch this video. Make sure you're pretty solid on everything up to this point. Monday, we will talk about the integrals. We'll go over that, answer any last-minute questions you have, and then we will start our exam. But if you do have questions, obviously let me know this weekend, and I'll be happy to get you an answer. I'll go with, now,